This is a sample of dinitrogen tetroxide, a compound which reacts very vigorously with many organic compounds. And today we're going to react it with aniline. We must pour the N2O4 rather carefully because it boils at a low temperature, and we don't wish too much of it to vaporize as it is rather toxic. Now we can add the aniline. Again, rather carefully because this is a fairly energetic reaction. And it usually proceeds even more vigorously once the tube has become warm. And you will see that this particular reaction is very reminiscent of a rocket fuel flame, which indeed it is. However, in the rocket engines which are used at present, aniline is not used as the fuel. Instead, unsymmetrical dimethyl hydrazine was used as the fuel in Apollo spacecraft, along with N2O4 as the oxidizer, and we can now demonstrate the burning of that particular fuel combination. It's necessary for us, first of all, therefore, to load the fuel tank. The hydrazine is the fuel, and here we have 30 milliliters of the fuel, which we'll now put into this tank. And you can rest assured that the actual loading procedure used by the Apollo technicians is rather more sophisticated than the one which I'm using here. However, there we have the fuel component now loaded, and we must now proceed to load the oxidant, the N2O4. It has been necessary to pre-cool the tank here because the N2O4 is very volatile, and as you will see, it will create a fairly large amount of fuming. It is also a rather toxic compound which it is inadvisable to breathe. Now we have both tanks loaded and are ready to fire.
Like Norman Logan's splendid model, a real rocket is also powered by chemical energy, and the source of this energy is the propellant. It usually comes in two parts: a fuel, like the petrol you put in your car, and an oxidizer, like the oxygen it burns in. To fire the rocket, these two components are brought together, and they react in a controlled explosion. But how are the components of a good propellant system chosen? Well, one criterion is pretty obvious. The reaction between them should obviously release as much energy as possible. It should be highly exothermic. There are other criteria, and we'll come back to them later. But let's start with this one. What makes a reaction exothermic? Where does the energy come from? To answer these questions, we need to look more closely at what happens on the molecular level when substances react together. The reactions you've seen so far are a bit complicated, so let's start with a simpler one. It's a combination that's been investigated by NASA as a possible rocket propellant, the reaction between hydrogen and fluorine. The hydrogen is in the balloon on the left, the cylinder on the right contains fluorine. Let's see what happens when we fire a jet of fluorine at the balloon. Well, Well, it certainly looks pretty exothermic, but I'm going to concentrate on what goes on in this reaction to see why it releases so much energy. Let's see the reaction again, in slow motion this time. We start with hydrogen and fluorine, and we end up with hydrogen fluoride. As you saw, all three are gases. But what you couldn't see is that each gas contains discrete diatomic molecules, a bit like this. Each molecule has two atoms held together by a single covalent bond. Now, when hydrogen and fluorine react together, the atoms in these molecules get reshuffled. For instance, fluorine starts off bound to fluorine, but ends up bound to hydrogen. So the net effect of the reaction is to break HH and FF bonds and to form HF bonds. And as a result, energy is released. So perhaps this is where the energy comes from, the breaking and making of chemical bonds. Now, a molecule of fluorine doesn't simply fall apart. It's held together by the FF bond. We've got to put some energy in to tear the two atoms apart and break the bond. And it needs a very specific amount of energy to do this. It's called the bond energy. For example, to decompose a fluorine molecule, that is, to break the FF bond, we've got to put in 158 kilojoules per mole. So the energy of the FF bond is 158 kilojoules per mole. How about the other substances in our reaction? Hydrogen and hydrogen fluoride. Why aren't the bond energies all the same? Well, the bond energy is really a sort of measure of the strength of a particular bond. The higher the energy, the stronger the bond. So it's pretty obvious from these figures that the FF bond is a lot weaker than the other two. But these values also tell us something else. If it takes 568 kilojoules to break the HF bond, what happens when I do this? 568 kilojoules are released. Bond breaking requires energy. Energy is released when bonds are formed. Now let's see if we can use these ideas to understand why our reaction releases energy. Let's suppose that 1 mole of hydrogen and fluorine are consumed, forming 2 moles of hydrogen fluoride. Next, we'll imagine that our reaction takes place by a series of steps, and we'll look at the energy change for each one. First, we break up hydrogen molecules, and that requires an input of energy. The value is just the energy of the HH bond. Next, we break up fluorine molecules, a further energy input. So it's cost us a total of 594 kilojoules to produce hydrogen and fluorine atoms. The final step is to recombine these atoms into molecules of hydrogen fluoride to form HF bonds. And this is the step that releases energy, an amount equal to twice the energy of the HF bond. So that's a total energy output of 1136 kilojoules. So let's summarize. The bond energies tell us the energy input to break HH and FF bonds, and the energy output when HF bonds are formed. Now we need to do a little sum. The overall energy change for the reaction is just the difference between the total energy input and output. Remembering that these figures are in kilojoules, I make that a total of 542 kilojoules out. The reaction is strongly exothermic. Well, we already knew that, but now we can see why. It's because this total is a lot bigger than this one, and that's because the products contain stronger bonds than the reactants. In this case, the HF bond is actually a lot stronger than both of the others, but the weakness of the FF bond does stand out. It's one of the reasons why the reactions of fluorine are usually very energetic. So we can summarize our findings. A reaction will be exothermic if weak bonds are broken and replaced by strong ones. So, a good propellant should have weak bonds in the reactants and strong bonds in the products. But what more do we need if we want to use an exothermic reaction for rocket propulsion? Well, a rocket engine is actually very simple. It looks a lot like this. Inlet pipes for the propellant, a combustion chamber, an exhaust nozzle. And there's really nothing inside. If I turn it around, you can look right down the exhaust nozzle through the chamber to the inlet pipes. And if I take the top off, all is revealed. The combustion chamber is just a hollow tube. The fuel and the oxidizer are injected into the chamber, and they must mix and react before the gases reach the exhaust nozzle. So that suggests a second fairly obvious criterion for a good propellant. The reaction between the components should be fast as well as exothermic. But there is a third criterion, and that's not quite so obvious. Inside the chamber, the chemical energy is converted directly to kinetic energy in the molecules of the products. The net result is a stream of hot, fast-moving gases which are ejected through the nozzle in one direction, and the reaction to this causes the body of the rocket to move in the opposite direction, for much the same reason that Newton's laws tell us this should happen. Well, for a rocket, the higher the exhaust velocity, the greater is the reaction on the rocket, and so the more effective is the propellant. So how can we increase the exhaust velocity? 2 more balloons of gas, but there is a difference between them. This one contains hydrogen, and this one carbon dioxide. Hydrogen has a lower molar mass than carbon dioxide. It's a lot lighter. But what do you suppose would happen if I released the gases in these 2 balloons? Here I've got 2 more balloons of gas, only this time they're fixed, so they can't actually move. The red one contains hydrogen, low molar mass. The yellow one contains carbon dioxide, high molar mass, and that's the only difference between them. Okay, now let's see what happens when I pull these 2 stoppers, both together if I can. Well, the light gas empties a lot faster than the heavy one. The exhaust velocity is higher, and that suggests that for a rocket, the lower the molar mass of the exhaust gases, the greater is the exhaust velocity, and so the more effective is the propellant. So, there are 3 general properties that any good rocket propellant must have. First, the reaction between the components must be highly exothermic. Second, it must be fast. And finally, the product should be gases of low molar mass. These 3 criteria were recognized by that pioneer of rocket technology, Wernher von Braun, and were exploited in Germany during the Second World War.
40 years ago, the position I'm in would have been one of the most dangerous that anyone could occupy. We're at the Duxford department of the Imperial War Museum in Cambridgeshire, and I'm sitting in the pilot's seat of a Messerschmitt 163. There's only ever been one manned operational rocket fighter, and the Messerschmitt 163 was it. Like most rockets, its propellant came in 2 parts, a fuel and an oxidizer. The Germans called the oxidizer T-Stoff, and it was pumped in to the aircraft through this filler cap immediately behind the cockpit. From there, it ran into one of 3 tanks. The main tank runs back along the fuselage from behind the cockpit, and there were 2 smaller 16-gallon tanks on either side of the pilot's seat. You can see that the pilot was hemmed in at the back and sides by tanks of T-Stoff. T-Stoff was an 80% aqueous solution of hydrogen peroxide, and it's extremely corrosive. What happened when during combat or an accident hydrogen peroxide leaked into the cockpit, well, that's unimaginable. But here's the first of a series of clips from some captured German film. It shows the effect of T-Stoff on an empty sack.
Nun ein Versuch mit einem organischen Stoff, der mit T-Stoff getränkt wird. Nach kurzer Zeit schon geht der Stoff in Flammen auf.
How about the fuel, the thing that the hydrogen peroxide oxidized? This was hydrazine, or more accurately, a solution of hydrazine in methyl alcohol. The Germans called it C-Stoff. Here's the C-Stoff filler cap. It's immediately behind the main T-Stoff tank. From there, the hydrazine solution drained down into tanks in the inner parts of the wings underneath where I'm kneeling. From the storage tanks, the T-Stoff and C-Stoff passed along the fuselage to the rocket motor in the tail. And it was in the combustion chamber under here that the hydrazine and hydrogen peroxide came together and reacted in a controlled explosion, producing nitrogen and steam. Let's see some film of that reaction.
Wie heftig die beiden Treibstoffe bei gegenseitiger Berührung reagieren, zeigt jetzt ein kleiner Versuch. Eine Schale wird mit C-Stoff gefüllt und abgestellt. Mit einer Pipette wird eine kleine Menge T-Stoff entnommen. Wenige Spritzer in den C-Stoff lösen schon heftige, explosionsartige Flammenbildung aus.
Now, we've already told you the general properties that a good rocket propellant must have. So let's see if this particular combination has got them. Let's start by looking at the chemical formulae of the two ingredients. Hydrazine, N2H4, and hydrogen peroxide, H2O2. You can see that the elements involved are nitrogen, hydrogen, and oxygen. Now let's look at the energies of some bonds formed between these elements. We'll start with single bonds. Here's a list of single bonds in order of increasing energy. You can see that the OO and NN single bonds are at the top of the list. They are very weak bonds. Near the bottom of the list comes the OH single bond. This is very strong. Now here's a similar table for double and triple bonds. In general, they are stronger than single bonds, and you can see that the NN triple bond is the strongest of the lot. So, OO and NN single bonds are weak. OH single bonds and NN triple bonds are strong. Even if we divide the NN triple bond energy by 3, we still get a value that's much bigger than the bond energy for the NN single bond. Let's look next at the equation for the reaction. Hydrazine, N2H4, plus hydrogen peroxide, H2O2, gives nitrogen, N2, and water, H2O. Now for the bonds in the reactants and products. There are single bonds in the reactants, including a very weak NN single bond and OO single bond. Now the products. Here there's an NN triple bond and strong OH bonds. Remember the bond energies. In this reaction, some very weak bonds disappear and they're replaced by very strong ones. Naturally then, the reaction is very exothermic, and because so much heat is given out, the water product is in the form of steam. This brings us to the molecular weights of the product gases. Well, they are pretty small. For example, both nitrogen and steam are lighter than air. So, the reaction is very exothermic, and the exhaust gases have low molecular weights. Finally, as you've already seen, the reaction is very fast. So, our 3 conditions for a good propellant combination are present. That finishes the theory. Now let's see some more of the practice. The Messerschmitt 163 was an aircraft produced in desperate circumstances. In 1944, the bombing of German cities by Allied aircraft was almost continuous. The Messerschmitt 163 was a rush job designed to stop that bombing. The rocket motor, the Walter 509, was very simple. It could be built in a fifth of the time it took to make a conventional aircraft engine. Here it is on a test rig. Besides being simple, the motor was also small, and the business end, the combustion chamber in the tail, was even smaller. It's only 50 centimeters long, and the maximum diameter is 30 centimeters. You could almost carry it away in the briefcase. The rest of the motor is just a pumping system. Each one of this cluster of 12 tubes carried either T-stoff or C-stoff from the pumps into the combustion chamber. If we look down the exit cone, you can see some of the inlet valves. The combustion chamber is just an empty tube. In there, the hydrazine and hydrogen peroxide mixed and exploded. The explosion produced hot gases which rushed towards us and pushed the aircraft forward. The takeoff, known technically as a sharp start, was the most dangerous moment. The rocket took off on a two-wheel trolley, which was jettisoned when the aircraft got 40 feet off the ground. Here, the trolley has failed to separate, so the pilot takes the precaution of emptying his hydrogen peroxide tanks. The aircraft's great strength was its high performance. The Messerschmitt 163 could climb 4 times as fast as an Allied fighter like the American Mustang. It could take off and intercept Allied bombers when they were only 25 miles away. Its top speed was also impressive. It could fly 150 miles an hour faster than the Mustang. Here, a Messerschmitt 163 uses its 230mm cannon to destroy an American B-17 Flying Fortress. But like all rocket aircraft, the Messerschmitt 163 had a big drawback. This was its endurance. The fuel ran out after only 7.5 minutes of powered flight. This made the pilot even more vulnerable, because he had to glide home with empty fuel tanks, a welcome target for Allied fighters. For Germany, the Messerschmitt 163 program was probably a mistake. The aircraft flew too fast for its slow-firing cannon to do much damage. It killed more German pilots in accidents than it did Allied pilots in combat. But from where we stand now, we can see that rockets like these were the forerunners of those used in today's space program.